All right, day 27. We are talking more about hypothesis testing today. A general overview of what we're covering. We will be working through the quantitative version of what we talked about on Wednesday. Namely, we are going to be working with, quantitative variables, which means using t-distributions. But the structure of it should feel extremely similar to what we did on Wednesday. After that, we'll talk a little bit more about what these p-values mean, as in what can they tell us and what don't they tell us. And then at the very end, we'll start laying some groundwork for our discussion on Monday, which is going to be about what can go wrong with this hypothesis testing. What happens if we come to the wrong conclusion? Okay, so let's work through a quantitative version of what we did on Wednesday. So just as a reminder, the procedure that we're doing for this applies for any hypothesis test we're doing. We'll be doing plenty of different hypothesis tests going on for the next couple weeks, but we typically always want to follow this format. All right, so the point of a hypothesis test is if we have a situation where we want to determine if the thing that we're observing is statistically significant. If it's sufficient evidence that something is going on, that there's some general trend that we need to maybe be paying attention to, the hypothesis test is designed to indicate if, hey, something's happening here. For example, we might be interested if a new drug actually does do better than some baseline measurement. Okay, the example I want to do for this quantitative hypothesis test is extremely similar to the question that we did last week, where we were trying to build a confidence interval around how many ounces of coffee we think that this coffee machine dispenses. Today, what we're going to be doing is answering a slightly different question, but with the same data. We still have these 20 data points, but now we're asking, is this evidence that the machine's average coffee dispensing is something less than the promised 10 ounces? Maybe the machine is advertising that it dispenses 10 ounces of coffee. Well, maybe we want to know if it's shortchanging us. Our null hypothesis should always be a statement about a population parameter. We know exactly what the sample mean or the sample standard deviation was. What we are interested in isn't what happened with these 20 cups of coffee. We're interested in the big picture. We want to know the population's parameter. Because we're dealing with a quantitative variable, we're measuring ounces of coffee, this is a quantitative variable, we want to be talking about mu. So mu is the population mean. I'm drawing the distinction between mu and x bar. X bar we can calculate from the sample, but what we're really interested in, what our focus is on the population's mean. So the null hypothesis should be that nothing interesting is happening, that we're assuming it's the status quo, that if the coffee machine says that it dispenses 10 ounces, let's just start off by assuming that that's true. We have an innocent until proven guilty mentality about claims like this. So our H naught, our null hypothesis, is that the average coffee dispensed actually is 10 ounces. The whole reason that we're running this hypothesis test is that we have a suspicion that the machine is shortchanging us. We have a suspicion that the actual population mean is something less than 10. So we're going to say that our alternate hypothesis is that the average coffee dispensed per cup is anything less than 10 ounces. In other words, we are doing a one-sided hypothesis test. Okay, so the model that we're doing, the particular type of hypothesis test that we're running, is going to be a one-sample t-test. It's a t-test because we're working with a quantitative variable. The one sample comes in because we're only taking one sample. Next week, we'll deal with situations where we're comparing two samples to each other. But for now, this is the only type of quantitative hypothesis test that we know so far. All right. I want to point out that one sample and one-sided are two separate notions. It's a one-sided hypothesis test because we're mainly concerned in situations where the mean is less than the advertised value. The one sample part comes in because we're only taking one sample. Two separate notions. All right, before we go any further, it's a good idea to check our assumptions that the situation that we're trying to apply a one sample t-test to is a suitable situation. And so I'd probably say that the first, maybe unspoken assumption is that we're dealing with a quantitative variable. It only makes sense to use one sample t-tests when we're working with quantitative variables. Okay, but the first main assumption that we're going to be checking is that our sample is random and independent. And I've clustered these two together. They're often broken up in other textbooks. But really here we're just saying that our sample is a representative sample of the actual workings of this coffee machine. In the prompt, we even say that it is in fact a random sample. This independent part, though, at least to me, is not immediately obvious. It could have been the case that maybe these coffee cups were measured late in the day when the machine had been running a long time, or maybe there was they all use the same type of coffee grounds, or, there conceivably could be something that is causing this sample to not necessarily be independent of each other, that these individual entries maybe are linked in some way. And if that's the case, then that's going to be messing with all of the logic, all of the inference we're doing moving forward. That said, given this prompt, I think it's certainly reasonable to assume that, at least for the most part, these individual entries are in fact independent of each other. So I would say that this condition is met, but it's certainly possible to come across one of these questions where we don't think that one of these assumptions is met. And this applies, again, to all of the hypothesis testing that we're doing. So as a general rule of thumb, if we come across an assumption that we don't think is met, if we're doing a question, if we're talking about a study that doesn't meet one of our assumptions, the general procedure is going to be to acknowledge it, to point out that, hey, maybe these cups aren't independent. Maybe something weird is going on. But typically we're going to still go through the rest of the steps and still run the hypothesis test, but maybe with a big asterisk next to it. So when we report our information, maybe we're saying, maybe this is what's going on, but we have these other considerations. Okay, so the other condition that we want to check for this one sample t-test assumptions is the nearly normal condition. So just as a reminder, we're using a t-test because when working with a quantitative variable, we're typically going to need some measurement of the standard deviation. We want to know what sigma is in order to be able to do a lot of our logic. We don't have that information. So rather than knowing what the population distribution actually looks like, we can use information about the sample as a proxy. So here we're going to be using the sample standard deviation to sub in for the population standard deviation. So whenever we do this, we have to account for the fact that we are chronically underestimating by using a different distribution. Rather than using our normal distribution, we're using our t-distributions. And then whenever we make this switch, whenever we switch over to saying, hey, now we're using t-distributions, we have to check the nearly normal condition. It has to be plausible that the population's distribution is in fact normal. How do we know what that looks like? Well, we don't. So again, we're somewhat approximating things, but we're going to use the sample distribution to address this. So typically the nearly normal condition, what it really wants to be talking about is the population distribution, but to satisfy this, to check this, we will look at the sample distribution. So I've got my 20 points here, my 20 cups of coffee. If I made a histogram of them, it would look something like this. Since this conceivably is a normal distribution, mainly it's unimodal and roughly symmetric, then this would be something that is certainly nearly normal. So this one actually looks pretty good. I would certainly say that this passes the nearly normal condition. Generally, these histograms of the sample can even be a little bit messy. It's only when they are notably bimodal or notably skewed that we start to suspect the nearly normal condition. All right, next section. What we want to be doing in this section is doing our actual calculations. Here our goal is to find the p-value. So just like last time, the p-value is the probability that, assuming that the null hypothesis is true, so in this case, assuming that our coffee machine actually does dispense 10-ounce cups of coffee on average, then what is the probability that if we go through this procedure, that if we take 20 cups, calculate the ounces in each of them, and find the average of that, what's the probability that the thing that we get is at least as unusual, at least as weird, as the particular answer that we got here? Okay, so for the sample that we actually ran, the average quantity of coffee, the average number of ounces of coffee, was 9.845. Certainly this is less than 10 ounces. The overall question is this significantly less? Is this far enough less that we suspect that 10 ounces is not the correct average? Again, to answer this, we want to find the probability that that this occurs. What's the probability that if 10 ounces is true, we just by happenstance get an answer that looks like this? Okay, now we're asking a probability question. We're in the world where the average amount of coffee per cup is 10 ounces, and we are imagining what happens if we again were to go and measure 20 cups. So typically the average of these 20 cups is going to be the same as the population's average. This is going to be typically something around 10. But if we were to measure 20 cups and the average amount of coffee in those cups was 9.98, that seems like a pretty small deviation. That's probably not that unlikely. The question that we have is, well, when we did this sample, we got 9.845. The question is, how unlikely was it to get this? What is the probability that if we were to do this again, that our outcome, or that the average of our new 20 cups is this weird or weirder? So we want to know the probability that, assuming H0, assuming that we're working in this framework, what's the probability of getting a result on this side, on the left, of the actual value that we got? All right, so this distribution is the probability distribution of what we expect the average of a certain sample to be. The center of this probability distribution is just going to be the expected value, or the mean, or in this case the same thing as the population's mean, of 10 ounces. Well, the standard deviation of this distribution, the standard deviation of this normal curve, is a little bit trickier. So our null hypothesis is that the average is a certain thing. So our null hypothesis is that this expected value is exactly 10. Our null hypothesis doesn't say anything about the standard deviation. So we're assuming that this is true, which allows us to say that, this distribution should be exactly centered here. But we don't really know what the standard deviation is doing. If we did, then we would be able to say that the standard deviation of this distribution is sigma over the square root of n. Here my n is 20, but we don't know sigma. So rather than working with this equation, we're going to replace it with the standard error. So the standard error, still measuring the probability distribution of the sample mean, the standard error is s over square root of n. In other words, we are estimating that sigma with the sample standard deviation. Going back to our original data, we can look at these 20 points that we actually found, our sample, and realize that our sample standard deviation, the standard deviation of all these points, ends up being 1.99. Again, we could plug this into R and run the SD function. It should spit out 1.99. So when we can use that to calculate the standard error. And then when we plug in these numbers, we should get that our standard error here is 0.0445. In other words, the standard deviation of this distribution, of the probability distribution for the sample mean, is 0.0445. So we can use these two numbers to ask, all right, what is the probability that a random sample lies less than a cutoff? This just then becomes a normal distribution question. So what we want to do is we want to convert this into a z-score, except we're not using z distributions. So the idea is exactly the same, but what we're going to do is we're going to convert this into a t-score, which again is really the same thing, but it's just a reminder that we're working with a t distribution. Okay, so this format should look very familiar. We're taking the point in question, subtracting the mean of the distribution, and dividing by the standard deviation of the distribution. In other words, we're asking how many standard deviations away from the center, away from the mean, is this point in question. So if we evaluate this, we'll see that our point in question is 3.49, so about 3.5 standard deviations less than the middle. So if this was a normal distribution question, then we could use the function pnorm evaluated at negative 3.49 to find the probability of being less than this, the area of this distribution less than a cutoff. Yeah. There are a whole bunch of different t distributions. We have to specify how big our sample size is. More specifically, we have to specify the degrees of freedom. Now for these questions, this is going to be the sample size minus 1, which in this case is just 19. So this number, the fact that our degrees of freedom is 19, together with our t-score, will allow us to find this probability. If we're using R, the function is pt, so rather than pnorm, it's pt, of the t-score in question. But then we also have to specify the degrees of freedom. So in this case, our degrees of freedom is 19. So if we used R to calculate this, we would see that our p-value is fairly small, 0.0012. So remember, this number is telling us that if it is in fact the case that the coffee machine dispenses 10 ounces of coffee per cup on average, this is the probability that we, just by happenstance, get a result like the one that we got. All right, so then last section, we want to state our conclusion. Because we just found a p-value that was very, very small, this is evidence that the situation that we saw probably wasn't just due to random chance. Such a low p-value makes it unlikely that this low sample mean was just due to sampling error, just the way that the sample was randomly constructed. As a result, we're going to reject the null hypothesis in favor of the alternate hypothesis and say that this is in fact strong evidence that the average amount of coffee dispensed by the machine is in fact less than the advertised 10 ounces. Okay, in the last little bit here, I wanted to talk a little bit more about p-values, as in like what exactly can they tell us and what can't they tell us. And the first point that I wanted to re-emphasize is that the p-value is really a conditional probability. In a sense, we're saying, okay, hypothetically, if we were to do this again, what are the odds that we get the same thing again, or something at least as extreme again? So typically we're looking at an unlikely outcome, and we're asking, well, how unlikely is it? Is this substantially unlikely? And we're doing all of this in the context of the null hypothesis. The whole time we are assuming that the null hypothesis is true, and then we're asking about probabilities. And the general rule is that if the particular observed statistic is so unlikely, if this probability is very, very small, then, well, yes, there certainly is a chance that it was just due to the way we measured our sample. But maybe a more likely explanation is that the null hypothesis was in fact wrong. So for our hypothesis tests, we have to draw the line somewhere. If we ran this hypothesis test and came to the conclusion that the result that we got happens 1 out of 4 times, that's not enough to throw out the null hypothesis. If instead it happened 1 out of 1 billion times, that's extremely unlikely. That's certainly enough to throw out the null hypothesis. But what about something more in the middle? Where do we draw the line? And last time I referred to this as a cutoff value, which is certainly how I think about it. But moving forward, we're going to give this thing a name. We're going to call this alpha. So this alpha is the cutoff value with which we're going to make a decision about H naught. If our p-value happens to be less than our pre-chosen cutoff value, then we're going to choose to reject the null hypothesis. For a very small p-value, we're rejecting the null hypothesis. If instead our p-value was bigger than alpha, if we had a reasonably likely observed statistic, then that is not evidence to get rid of the null hypothesis, so we're going to fail to reject the null hypothesis. Again, as a reminder, we're not confirming the null hypothesis, we're not accepting it. All we're saying is that the observation that we made isn't enough to get rid of it. Okay, so these are the only 2 things that can happen, and it's very much a binary scale. Having a particularly low p-value makes us more confident about our choice to reject the null hypothesis, but it's not an indication of how strong of a trend we're dealing with. So here's what I mean by that. Let's pretend we have 2 completely separate experiments. On one side, we are trying to tell if drug X is better than a placebo at, let's say, reducing blood pressure. And completely separately, we're also asking if drug Y is better than a placebo at reducing blood pressure. So however we wanted to phrase that, depending on what exactly we're measuring, our null hypothesis for each is going to be that, this drug isn't anything special. It's just not actually doing anything. Our null hypothesis is that nothing special is happening, whereas the alternate hypothesis is that there actually is an effect. So let's say in this first example, we ran this experiment and we saw a p-value of 0.01. So this is less than our predetermined cutoff value. It's less than alpha. Therefore, we are going to reject our null hypothesis. This is evidence that drug X does a better job of reducing blood pressure than a placebo. Similarly, on our other experiment, we could have gone through the whole hypothesis test procedure for drug Y. Maybe we find that its p-value is 0.0001. Okay, so over here, yeah, we certainly reject the null hypothesis as well. This is also evidence that drug Y is an improvement over a placebo. So in both situations, we're going to reject the null hypothesis in favor of the alternate hypothesis. The point I'm making is that this information is not evidence that drug Y is any better than drug X. All this is saying is that we are pretty confident, we are very confident about our rejection over here, and we're also confident about our rejection on the other one. The fact that we've got a particularly small p-value on one side is not an indication of any magnitude of separation for drug X compared to drug Y. All we're measuring here is the drug an improvement over a placebo or not? There are no degrees here, it's just a binary yes or no.